you hear these words, what comes to your mind? You can say on chat, what comes to your mind? Anything at all. Okay, so Shweta Rai said sour taste. Anything else that comes to your mind? And we are all familiar with these sour and bitter substances. Then one person had said H plus ions and OH minus ions. Very good. Uma Sharma has said burning. Uma, what kind of burning can you say? Roji is saying dangerous substances. Yes, acid burns. Acha, oh, you mean burning that in that sense? Yes, acids corrode. We know that they are strong and they corrode. They are corrosive. Excellent. And so people have talked about their corrosive property, particularly of acids. Even bases can be corrosive, uh, but uh, but people have also talked about sourness and bitterness and acidity. We are familiar with that word a lot because in usual life we get acidity because of our stomach acid, and so acids contain hydrogen ions, correct? And so somebody has said soap. So soap we know is basic or alkaline. So it's mostly their taste and the ions necessarily contain. And somebody has said something which turns blue litmus into red. So yes, friends. So we all have some prior knowledge about acids and bases. So, but it's good to think of acids and bases when you think of, when you start thinking of water. Water has a very deep relation with acids and bases. Somebody said neutralization. Oh, is there an audio problem? Can others tell me? I mean, is everyone having an audio problem? Am I audible? Oh, others are saying no. So then, I mean, we have a suggestion for my colleagues will put a suggestion for those who are having audio problems. So base have a bitter taste. Yes, absolutely. But let's see what is the relation of acids and bases with water. So friends, let's first look at water in a chemical sense. So, so water we know is one oxygen atom combined with two hydrogen atoms. And I mean, if we look at the bonding pattern, there is a particular kind of, I mean, like, of course, this is sharing of electrons through which this bond is created between oxygen and hydrogen. But that bond has a peculiar character. So I will request Manisha to show it on the uh, on a board, and she will write and show it. And for that, we will be showing through tab. Uh, so I will spotlight tab, and so just give me a minute. I will spotlight tab, and those of you who are seeing from a mobile, those people can pin tab. There's a window called tab tab. So tab has to start its video. They are just setting up. So okay. I will spotlight. So so Manisha is right now showing. Manisha, there are spots on the. They are already spots. They will interfere. So if you want to write, no, if you want to write on the other side, take chalk. As Priscilla said, they are. This is HOH. That's correct. But they are combined in a specific manner, which we are just showing. So Manisha is just showing it. So it's like no, not that way. You have to show both bonds and how the electron pair is shifted. So we know that H and H, she is showing the H electron with a cross, and O electrons with dots. So we know that oxygen has 6 electrons in the outer orbit and hydrogen has only 1, and which she has shown as crosses. So hydrogen electrons are shown as crosses just to differentiate, and oxygen are shown as dots. So now she will show the combination, the sharing. So how they are shared. So the hydrogen, I mean, this is how sharing happens between one hydrogen and one oxygen. So what happens that one electron pair gets shared between both. So that now oxygen also has 8 in all. So you see oxygen has 6 dots of its own and 2 crosses, which means oxygen completes its requirement of 8 and hydrogen completes its requirement of 2 in its outer shell. The first shell, so 2, and oxygen requires 8, so that also gets completed. So ideally, water molecule should have been completely neutral, but that's not what happens in reality, because oxygen is much more electronegative, or let's say it attracts electrons much more because of a larger nucleus and larger number of protons inside. Oxygen pulls the electron towards itself. So this hydrogen electrons get pulled more towards oxygen. So, so Manisha, can you show that? I mean, this X you can take, this cross you can take closer to oxygen. So, I mean, oh, you didn't need to rub it anyway. All right. You can make it a pair. So a pair one above the other, like that will be easier. So it's like this is sharing or pairing, but the sharing actually gets pulled, the electrons get pulled toward oxygen much more. So hydrogen, from the hydrogen side, they come towards the oxygen side. So therefore, what happens is, see, water shouldn't have been a polar molecule. What we mean by polar molecule is it shouldn't be having extra charge on oxygen or on hydrogen, because it's only sharing happening. It's not an ionic bond or electrovalent bond. It is sharing. It's covalent bond. But what really happens is, I am now removing. You can show the oxygen with a circle as well. So oxygen has its 8. I mean, no, what I mean is like the way you put circles around hydrogen. So this is what oxygen is like. So the only thing that now she's shown is that the hydrogen electrons, the two crosses have gotten pulled towards oxygen. So I'm removing the spotlight, and I'll get to my screen. So on the screen you can see that because of this a little shifting of the electron cloud or pulling of the electrons, the oxygen develops an extra negative charge. What is written here is delta negative. Delta negative simply means that it's not a full -1 charge, -1 or -2. It's a small negative charge, and hydrogen has a small positive charge. And surprisingly, water does show like this polar character. I mean, like it gets attracted by anything else charged. Water is somewhat a little charged. Water should have been a completely neutral substance, but it is not. It has its molecule itself has one slightly negative end and one slightly positive end, or it's a slightly polar molecule, right? So that's what we are trying to show. And therefore, some part of water automatically ionizes. See, water shouldn't have ionized because water is not an electrovalent or ionic compound, but water gets ionized, which means some amount of water breaks up into H plus and OH minus. Only some amount of water breaks up into this. So not only there is this water breaking up into H plus or OH minus, some H plus and OH minus will also recombine to form water. So this happens both ways. So breaking up of water into ionic forms and ions combining to give neutral water also happens. So we see that water, this is a natural process which keeps happening in water. But this number, the number of water molecules which break up like this is really small. So, and I'll just come to how small it is. So you see that H2O gets broken up into uh, Manisa Assis, please keep admitting people because people are constantly coming. So, water breaks up into H plus and OH minus. But since think of this H plus ion, it's essentially a proton. I mean, a single electron has been knocked off, so it's essentially a nucleus or very small nucleus with just one proton or one or two neutrons. So just a single proton, it cannot stay, let's say, separately. It cannot exist. It's very hard for it to exist separately. It typically joins up with another water molecule and makes H3O. And you can see H2O plus H, along with H plus will make this hydronium ion. It's called H3O ion. So that's how, like, so there'll be one H3O ion with one plus charge and OH ion minus ion with one minus charge. So that's the situation with not all water molecules, but a few water molecules do this naturally, always. So the same thing we have now shown visually. Okay, Priscilla has said I should repeat the last sentence. So what I was saying was, friends, that if you have understood that why a water molecule breaks up into H plus and OH ions, further to this, I'm saying that think of H plus ion, and H plus ion is just a hydrogen nucleus. Hydrogen had only one electron, which has been knocked off. So it's just the hydrogen nucleus, which is often a single proton or single proton plus neutron or single proton plus two neutrons. Basically, it's like a very small nucleus, which cannot. I mean, it doesn't actually remain single in nature. Doesn't exist by itself. It's even in like water, even in a liquid, it cannot exist by itself. Typically it joins with another H2O molecule. So one H2O with another H plus becomes H3O plus, this ion. Instead of H plus, it becomes H3O plus ion, which we call as hydronium ion. Is it clear? Okay, audio is breaking. Is it breaking for everyone? So is there any question so far? Please give a suggestion to a person who has an audio problem. They will need to check their own device, or they can like drop off once and come back again. So please write that. So any questions, friends, so far? If what is written on the screen is clear, then I will. Rajesh is saying that it's not working. Rajesh, you will have to check your internet connection or your device, because if the problem is not from our side, then it will have to be on your side. Okay, Priscilla has asked, in certain fractions of time, does water show acidic or basic properties? Priscilla, I'm soon coming to that. I'm very soon coming to that. First, I'm saying that this property neutral water has. Normal water, a water which does not have acidic or basic character, has this property. A very small quantity of ions would break up like this, right? And how acidity and basicity develops, I'm soon coming to that, right? So is there any other question? And if you think I'm going fast, please stop me whenever you want. Srijana has asked, why doesn't hydronium ions be formed in large amount? So, friends, because if you see what we were showing on the board, that actually there is like covalent sharing. It's actually, water is not an ionic compound; it's a covalent compound. So, water shouldn't be breaking up into H plus and OH ions. We know that, no? We know that in covalent bonds, this breaking up into ions does not happen. I mean, if you think of, let's say, carbon dioxide, um, so carbon dioxide will not break up into C plus and no, okay, C plus and O2 minus. It doesn't break up like that. Not every some covalent bonds or some molecules formed through sharing will have a little bit of this charge developed. And because of this charge developed, I mean, this will be there on all molecules, but a few molecules will actually break up, which means oxygen will take away the electron completely. Oxygen will take away one electron completely, and we will have this O and H remaining. So one OH ion will remain, and one H plus will break off. So one hydrogen will lose its its electron completely to OH and will break off to make this combination, which we are saying that, which is these two ions. It doesn't become like two H plus ions and one O double minus. It becomes one H plus and this OH minus. Why it happens, friends? It's got a lot to do with ionization energy and like higher level of chemistry, which we cannot get into right now. But basically, so as Priscilla is asking, not all molecules break during ionization. No, very small number does this. What we are showing on the screen, very small number. I'm soon coming to how many do this, because this is very deeply connected to what we mean by acidity and basicity, right? So I'm coming to it right away. So see, this is the same thing we have shown in as pictures here. So see, one H2O will be the red is one oxygen, the white ones are hydrogen. So water, both these water would be neutral molecules, but instead some of them will break up like this, H3O plus. So one oxygen with three hydrogen and with one positive charge, and one OH, oxygen and hydrogen. So one with, because of one extra electrons here, one negative charge here, one less electron, so one positive charge. So far good. I mean, if this is clear, friends, some of you at least will have to say yes, and then I will proceed. I will answer Priscilla's question. Okay, friends, but feel free to stop me anytime. Anytime you think that it's still not clear, please feel free. So, this is not a usual class, so you can always stop me and ask. So sorry. As the screen says that not all water molecules break into this, very few do. So how much of water breaks into this? I'm talking about normal ordinary water, right? So this is like, we see that roughly 1 liter of water has so many molecules. We have deliberately put in like green color here. So it's like, because it is like 3 crore. I mean, this number is like 3 and 3. So this is 8 zeros. So it's like, I mean, it is like 24 zeros. So we have deliberately put it as 888. So this 8 zeros in our country is used as crores. In other countries, this will be called as 10 million. We call it 1 crore. So this is 3 crore, like 10 to the power 24. So 1 liter of water, we have deliberately done this. You'll soon see why. So 1 liter of water has this many molecules, roughly 10 to the power 24 molecules. And out of these so many, the number that breaks up is 1. 1 out of 1 crore. So see, sorry, it's like one molecule out of 1 crore breaks up into H plus and OH ions, right? So that was not 3 crores. That is like, I mean, we don't have a name for it, but it's like 20 to 10 to the power 24. But I'm saying out of 10 to the power 8, one molecule breaks up into H plus and OH ions. Uh, so we can, if we try expressing it like in other numbers, you have to keep admitting people. If I do it, it like disturbs. Yeah, yeah. So because it appears on my top, no, and yeah. Uh, so if only one out of these many break, so we can also write it as 1 divided by this much, 1 divided by 1 crore. So this is, we can also write that, are there 7 zeros? Yeah, there are 7 zeros. Sorry, I was saying 8 zeros. There are 7 zeros. So sorry, I was mistaken. It is not 10 to the power 8, 10 to the power, this is like 7 zeros. So this can also be written as 1 into 10 to the power minus 7. So this is what happens in normal water, that out of the concentration of hydrogen ions, H plus ions, is 1 into 10 to the power minus 7. Which means out of so many molecules, only one will break up into ions, which is a very, very, very small number actually. You can see that very small portion of water naturally breaks into H plus and OH ions. And this power, here this power is 7, this is what is known as pH. So I mean, when we say, we have heard about a pH scale. So what is pH? So it is this power, and the negative is not attached to it. It's not generally written. It automatically means that this is negative power. But so when you have pH 7, we say no, neutral water has 7 pH. What we are saying is that basically out of 10 to the power 7 molecules, only one is breaking up into ions. Only one is ionizing. So this is what pH is telling us. It's essentially telling us the number of hydrogen ions. How many hydrogen ions are present in water molecules? Are you with me so far? I mean, is there any other question? So now can I proceed? Okay. So friends, for children's sake, I mean, numbers get very, very frightening and disturbing. I mean, especially large numbers. So we have deliberately put it uh, in colors, in circles, so that children can understand this idea. I mean, I would recommend this for only 9/10 children, not earlier than that, because before that, children don't even know ions. But for 9/10 children, you can represent like that. So you see, if we say that the pink is the H plus ion and green is the ordinary water molecule, so then this concentration is 1 out of 10. So, so this is 1 in 10. So that means pink is 1/10. The concentration of pink is 1/10, which we are showing as hydrogen ion. And we will write it as either 0.1 or 10 to the power -1. So what will be the pH here, friends? pH would be pH would be 1. So this is 1 pH. And you can see that 1 pH means extremely high concentration of this hydrogen ions, because earlier we were talking about in neutral water, we were talking 1 crore, there was a single one, and here 1 in 10. So it's extremely high pH concentration. So we will say that this is pH is 1 and it's very, very highly concentrated hydrogen ions. Very, very high concentration. And we have shown it the same thing in 100. So you can see in 100, this will be like, oh, here we have seen shown, is this 100 or 50? No, 100. No, it's 50, right? 50. So in 50, there are 5. Friends, somebody is annotating, which means you are writing on the screen, maybe not deliberately, but I'll have to just stop that, because otherwise it becomes disturbing for others. Okay, so this is like 5 and 50. Suppose we were to make it now 1 in 100. We first showed 1 in 10. Now this is, we have put 100 green circles and I mean green balls, and out of that only 1 ball is pink. So now can you guess the pH? What would be the pH now? So some people are saying 1, some people are saying 0.1, some people are saying some people have said 2. We will show the same thing mathematically. This will be 1 out of 100, 1 divided by 100, which we would write as in ordinary maths, we would write it as 0.01 or 1 into 10 to the power -2. See, you will have to think in terms of powers or exponents, like in powers. So in powers of 10, the power, if you want to represent it as power of 10, this will be 1 into 10 to the power -2, which means pH would be 2. So pH 2 means that means this is much less than the earlier pH. What we were showing here, the hydrogen ion concentration is much less. You can see 1 out of 100. So it is, hydrogen ion concentration has become much less, 1 in 100 instead of 1 in 10. So change of 1 pH means it's a full order changing, like from 10 to the power 1, it has become 10 to the power 2, or rather 10 to the power -1 to 10 to the power -2. So 1 in 100. So actually we are proceeding by powers, right? pH scale proceeds by powers. So there's a huge difference between 1 pH and 2 pH. Like much less concentration. 1 pH would be very, very high concentration. pH 2 is definitely lesser. So it's like 10 times less. So 10 times lesser concentration. So there's a great change now. So this is pH is 2. Yeah, so as those people who are writing 0.01, you are correct. But as soon as you say, you express 0.01 into powers of 10, it becomes 10 to the power -2. So, friends, I would request that please write that down on a piece of paper before saying it, because if we think of it mentally, we get confused, because we are not used to thinking in terms of powers of 10, right? So it will be good if you write it on a piece of paper, and then it's clear, right? So friends, so far no problem. Friends, it's pretty hard to wrap our heads around big numbers, even for adults. It's not only with children, like one has to think very carefully and very hard before when we come to such large numbers. So Priscilla has said, I repeat once more. So Priscilla, okay, I'll do the same thing which I started with, because this is an important argument, friends. So we began with saying that, just a sec, friends. Um, so we said that only one out of 1 crore, one molecule out of 1 crore molecules breaks into H plus and OH plus minus ions. So actually pH is hydrogen ion concentration, right? So for ordinary water, hydrogen ion concentration would be, like we said, 1 out of 1 crore molecules. So if we write it in other words, 1 divided by 1 crore. And if we want to write it not as a fraction, we want to write it into powers of 10, it will be 1 into 10 to the power minus 7. So this power of 10 is expressed as pH. So this pH is just this number without the minus. I mean, minus is assumed there. So this is like, this power 7 is known as pH, and this is the power, this is the pH of ordinary neutral water. So pH of neutral water is 7. What it's saying is, when we say that ordinary water is 7 pH, we are saying that the hydrogen ion concentration is 1 into 10 to the power minus 7. Right? Now the same thing I'm trying to show. Now, like I'm going in a reverse direction, starting from 1 pH. So I mean, for ease, I'm doing this for ease, because for if we draw 1 crore molecules on the screen, you'll not even be able to see those dots. So I'm starting with 1 in 10. So suppose there was 1 hydrogen ion in 10 water molecules. So if you write it in mathematical terms, this will be 1 in 10, which can be written as 1 divided by 10, right? And in powers of 10, this will be 1 into 10 to the power minus 1. And therefore, pH here would be 1. So 1 pH is this much hydrogen ion concentration, which is a very, very concentrated hydrogen ion. I mean, like we call these acids, of course, but this is a very, very concentrated, very high concentration, which is just shown on the next screen. Just look at it. In just 50, you have 5. So, I mean, earlier in neutral water, in 1 crore you have 1, and here you have 1 in 10. So that's very, very high concentration. This would be a very high concentrated acid, highly concentrated acid, this one. And we will say this has a pH of 1. And now from there I have come to 1 in 100. Here I was 1 in 10. Now I am coming to 1 in 100. And if I write it, it will be 1 divided by 100, expressed as a fraction, but expressed as a decimal, this will be 0.01, or expressed as powers of 10, this will be 1 into 10 to the power minus 2. So the pH here would be 2. So the pH is 2, and one can see that the hydrogen ion concentration, these square brackets actually represent concentration. So wherever we are saying these square brackets, it means automatically means concentration. So concentration of hydrogen ions is now 10 times less from here, from our earlier stage. From here to here, you can see it's 10 times less. pH has increased. pH has become 2, but the hydrogen ion concentration is 10 times less, far less. Earlier it was 1 in 10, now it is 1 in 100. Right? So, so far, is this clear? So it's like pH goes in reverse order. More pH means less concentration. Less pH means high concentration because it's a negative power. Right? And now, this is what a colleague did. He put now 1,000 dots here, and out of 1,000, one single one is hydrogen ion. So this is 1 in 1,000. So can you please write it for yourself and tell me the pH? Those who have a little confusion, just write it. Writing will make it clear. If doing it mentally at times confuses, so just write it. Yeah, so the pH is 3, but anybody who is getting a little like confused because it's like 1 upon 1,000, which you write as 0.001 or 10 to the power minus 3. Srijana, you forgot the 1. You said 0.00. Yeah, it will be 0.001. So 10 to the power minus 3. So the pH is 3. So pH has become 3. So now you see the concentration has reduced even further. pH is increasing from 1 to 3. The concentration has become less and less and less. Yes, 0.001. Yes. So that's how pH scale goes as it increases. So an increase in pH number means, will mean what? Now, more hydrogen ions or less hydrogen ions? pH number increases. So will it be more or less? Less. Hydrogen ions are now decreasing as you go ahead. As pH increases from 1, 2, 3, 4, 5, 6, 7, less hydrogen ions, consistently less, and therefore we finally reach 7, where hydrogen ion concentration is 7, which means 1 divided by 1 crore, 7 zeros. And we say water is neutral. Neutral does not mean that it has no hydrogen ions present. These are the hydrogen ions present in neutral water, natural water. When water doesn't have lesser or more, this is what nature has. So in nature, as Deepak is saying, acidity is decreasing as pH increases. So here at 7 pH, we are saying it is 0 acidity, no acidity, neutral water. But even in neutral water, we know that we are seeing that small amount of pH ions are present. And beyond this, pH, when it rises beyond 7, which means even less hydrogen ions. Hydrogen ions will decrease even from normal water. HN Pradhan is asking about NaCl. Pradhan, this is a salt. I'll soon come to salts. Right now, I'm only talking about acids. In fact, I have not defined acids. I'm only talking about hydrogen ion concentration. Right? So, the same conclusion is written here. Even if it seems disturbing, there is nothing. It's like zeros twist our minds. But we tried to present it in such a way. If this is confusing you, you can simply forget about it. See, because we had said one out of crore. So what we have said is 100 out of crore will make it 10 to the power minus 5. 1,000 out of crore will make it 10 to the power minus 4. So till we are less than 7. So in a crore, if it is 100, then it's 10 to the power minus 5. In a crore, it is 1,000, it will become 10 to the power minus 4. But if we go more than 7, Now this is 1 out of 10 crores. It will become 10 to the power minus 8. So 1 out of 10 crores, 1 out of 100 crores is 10 to the power minus 9. So which means like if you go beyond, okay, so Deepak Khatibara has asked, why only up to 10? No, we don't go only up to 10. We go to power of 10 to the power minus 14 also. But why not minus 15? I think, I mean, my sense is that maybe it doesn't exist in nature. I mean, beyond 10 to the power minus 14, uh, nature will not allow, like the breaking up into H and OH and reverse joining also carries on. So there's like, it's two-way. Some break up, some join back. I think I had, there was this was on their one screen, no? Breaking up and joining or no? No. No, it has not there on the screen so far. Maybe few in further we have shown, but uh, so so it's not easy to calculate. See, normally we don't calculate H plus ion concentration because it's like uh, unless like okay in higher level chemistry it's needed, we don't really calculate. We simply specify the pH, and it gives us just a number series from 1 to 14. So you hear the word pH 7 and you say it's normal water. Below pH 7, it's acid with high hydrogen ion concentration, and as the pH becomes less and less, hydrogen ion concentration increases more and more. So like an acid with 2 pH would be a very concentrated acid as compared to an acid which has 4 or 5 pH. So basically below 7 all acids and above 7 all bases. So just this number series, simple. And also we use indicators to handle for use of pH scales. We have our indicators. Uh, so either we use this 1 2 3 4 5 6 going up to 14, or we use indicators. So acids and bases are kind of estimated using these two things. And now Manisha will show many kinds of indicators. We have this beautiful universal indicator also. I'll just kind of just give you a sense of universal indicators. A universal indicator is interesting. It's not normally find it in nature, but human beings are clever. So they combined many organic dyes together in such a manner that neutral will give you this green color, as you like pH 6 will give you lesser green, 5 pH will give you yellow, 4 pH will give you orange, and 3 pH will give you bright red. Similarly 8 pH will give this blue, 9 will give darker blue, 10 a still very dark blue, and then purple. So we get a rainbow. We actually, they are close to the rainbow colors, the natural rainbow colors. It's the pH scale or indicator has been created like that. We will also show you that universal indicator. So Manisha will show you many kinds of indicators. I'm stopping share. I'm also uh, to tab pe karu, Manisha. And Manisha, will you be speaking or I speak? So Manisha will speak. So Manisha, you will have to take off your mask, and I will just. So friends, give us a minute. I will. Manisha will be speaking also. Um, just a sec, Manisha. I'll spotlight tab. So I have spotlighted, and you can also uh, pin tab. Just a sec, Manisha. A question is come, how does OH concentration increase after 7? I will come to that question very soon.
we have three different litmus papers. First is red litmus paper. Another one is blue litmus paper. And then we have pH paper. So we are going to use one by one to show. We are going to use
अब दे हो गया अब शायद हाँ हाँ ठीक है यहाँ से लेते हैं so we are going to use हमारे okay. We are going to use blue litmus paper and then red litmus paper and then the pH paper one by one to show indicators. This is acidic solution, HCl solution, and this is basic solution, NaOH solution. हाँ कौन है so this is HCl solution, that is acidic solution. हाँ एक बार पूछ we are going to use red litmus paper. Okay, we are going to put red litmus paper into the solution to check whether it changes or not. And then again, we are going to use a blue litmus paper. As you can see, red litmus paper does not change its color, but blue litmus paper changes color. So as you can see, blue litmus paper changes into red in color, whereas now we are going to using a basic solution, that is NaOH. Again, we are going to check with red litmus and blue litmus. The color of blue litmus paper does not change, whereas red litmus paper, you can see red litmus paper change into blue. ब्लू तो ये सेकंड ब्लू नहीं ब्लू है एक blue litmus paper does not change its color. हाँ कैसे
friends, as you can see, मेरी आवाज आ रही है? Can you hear me, friends? Actually, Manisha is not very close to the device, so the voice is not clear. See, what she did was first put one blue litmus and one red litmus in an acid solution. So in an acid solution, blue litmus turned red, but no effect on red litmus. वो दिखाना पहले जो किया था पहले जो किया था. See, first she put red and blue litmus both in an acid solution. So no effect on red litmus, but blue litmus turned red, as you can see. पारुल जो मैं बोल रही हूँ वो दिखाओ. तू ले ले. Then after that, the second case, she took where NaOH is written. She took NaOH solution, which is an alkaline solution, basic solution. The blue litmus remained blue. Actually, it became darker blue, but the red litmus turns completely blue. So very clear difference on the red litmus. So actually, as you know, litmuses work reverse. In acids, blue litmus will turn red, and in bases, red litmus will turn blue. So they have this reverse impact. Okay, so after this, now Manisha is showing a universal indicator paper, which is like, you can see it in the yellow color. Now she will dip it in acid. Let's see. See, it has turned bright red. And for this bright red color, she will match it with a scale, colored scale. So the colored scale normally comes with the strip itself, the universal indicator strip, and we have to match the color on the scale. So here it is matching with 2. It's closest to 2, so we can say the pH is 2, right? Which means a pretty strong acid, right? So as you can see, show the scale once more, the full scale, show it on camera, full scale. Close it, bring it close to the camera. So you see, so you can see this pH scale here gives different colors, and for each color, the pH is written from 2 to 10.5. So this is how this strip comes. So the color is indicated. I mean, what color will indicate how much pH, that's written. So you simply have to dip it in a solution, and and by matching color from this this indicator, you can make out whether it's acid or base and whether it's strong or weak, right? Yeah. Now Manisha will show this in the base. So she'll dip the indicator strip, this universal indicator yellow strip, she will dip it in a base and show you. So now she's showing it. Oh, but it has become. Acha, you I have to spotlight you. Wait. Just a second, friends. Give me a minute. I have spotlighted Asis's device. So Manisha is showing, she dipped it in a base, and you can see the color is matching with either 10 or 10.5. What do you think, Manisha? Is it 10 or 10.5?
10.
So Manisha thinks it is 10.5. Yes, it's closer to 10, not as like dark as 10.5. So this is 10. So that means this base has a pH of 10. So universal indicator is a very good thing to have in a lab because I mean, just by color, you can judge whether it's how strong, whether it's acid or base, and how strong the solution is. Now, Manisha is utilizing, okay, she's doing the same litmus test with using a solution instead of a paper. So you have litmus solutions also. So she will put litmus solution in HCl. So she has put blue litmus solution, and see, as she puts, it's constantly turning red. I mean, first show the color of the solution, Manisha. No, color of the litmus solution. This is litmus blue. So can you see the color? Actually, it's a plastic bottle, not showing color very clearly, but it's like blue solution. But as she keeps putting it, yeah, the color is quite blue. But as she puts it in an acid solution, it constantly turns from blue to red. And now she will show a red litmus solution. Yeah, this is very clearly visible. Now a red litmus solution. So see, it's appearing not very red. You'll have to put one drop on the white surface. Show a drop on the white surface. Yes. So people, as we can see, it's a red litmus, but when she puts it inside a base, it immediately turns blue. So whether you use a litmus paper or litmus solution, it doesn't matter. Both give the same test. And these are natural dyes, actually. These are organic dyes. They are taken from actually lichens, I mean, from some natural substances, rather plants. Yeah, lichen is not even exactly a plant, but yeah, from lichen, these are derived. So, and they naturally show this change in color. Now, probably Manisha will be showing, Manisha, will you be showing flowers? Okay, first we will show universal indicator, then we will try with flowers. See, a lot of flowers also show change in color with acids and bases. May not be very clear. Sometimes very good, sometimes not. We have a few flowers, but first she will show with a universal indicator. So, Manisha, do you need some time? Okay, she's ready. As Priscilla has said, lichens are association between algae and fungi. Yes, thanks, Priscilla. So here she has the universal indicator solution. We saw the paper earlier. This is a solution. Its color is, what is the color? It's like blue-green. Put a drop on a white surface for us to see. So this is kind of, I can't even make out the color. It's reddish, probably. Greenish. She's saying greenish, but the surface must be having some acid or base. So on the surface, it's turning into another color. Doesn't matter. Yeah, it is greenish. So there was some acid, therefore it turned bright red immediately. So it's a green color colored solution. And now she will, what Manisha is going to do is like make like seven beakers with different. So Manisha is saying first she will drop the indicator in just the acid and base she has to show the color. So look, in acid we are getting a bright red color, and in base it's getting a strong purple color. Just match it to your strip or your scale. So you can see the left hand side must be 2 and the right hand side is 10.5 or something, 10 or 10.5. It's like strong purple. But now she will actually create a range of acidity and basicity using 7 beakers. So the central beaker will be plain water, and 3 on the left hand side would be acidic, and 3 on the right hand side would be basic. It requires some amount of time, so we will let her do this. Yeah, as Prakash is saying, the color was crimson red, showing that the acid was reasonably strong. And we will show you bright like flowers also, if we can. See, flowers work sometimes, but sometimes they don't work very well, depending on what flower it is. So we've just got the flowers which we had in our surroundings. Some flowers, like some red and blue flowers we have got. And also we will show haldi or turmeric, which is an excellent indicator for bases. So, okay, Rosie is saying geranium works well. Okay, I didn't know that. So, but geranium is not available around this place. So, and we will show turmeric also soon. So turmeric is available in every household. That's why it's an excellent indicator to use. So, oh, Pema is saying China rose works well. We have a China rose. We'll try. So, but whenever we have done this session, I mean, flowers have given some color change, but not necessarily very clear color change, or not one type of color change. Like, it's not like litmus, not as clear as litmus, that red turning to blue and blue turning to red. Yeah, they just give a different color. Hitain is saying, can't see the screen. See, we have deliberately, she's doing some preparation. So currently, we have not switched on the video. पहले करेगी. So because this 7 colors requires some preparation, so she Manisha is saying she'll show turmeric and flowers first. So we have a China rose or hibiscus, so we'll try. A vinca flower shows good results. Vinca, I don't even know what flower it is. So so right now there is some turmeric in a dish in which what are you dropping? She's dropping some acid into the turmeric, and she dropped, and we can see no color change. Turmeric just got wet. That's all. I mean, the color change is only the color change you will get for wetness. But now she will put a base, which like alkali, she's putting NaOH, and see the bright red color, almost the color of blood. In fact, like you can use it to imitate blood, but very nice change happens. Even with soaps it happens, because soaps are also bases. Most soaps are, soaps and detergents are basic. So that's why this bright red is created. And in fact, some of you may know that this turmeric haldi is mixed with raw lime, kacha chuna, raw lime, CaO, and this bright red color that we get. Actually, it is CaOH, sorry, CaOH, kacha chuna, which we get in pan shops in North India. I don't know whether it's available in Sikkim or not, or whether people eat pan at all. But in pan shops, you can get CaOH, and if you mix that with turmeric, you get this bright red color. And the same thing is called as roli, which is used in puja here. At least in a lot of Hindu homes, it is used for puja, what we call as roli. So roli is essentially turmeric mixed with slaked lime or CaOH. Oh, so Deepak is saying pan is very famous here. So in pan shops, you can get that tuna which is actually calcium hydroxide, the tuna which is put in pan. So that with turmeric gives a very beautiful color, this beautiful bright red color. Now Manisha would rub the flower on some paper. See, instead of directly putting it on flower petals, it's good to rub it on paper. So she will rub the flower on paper, and then put the acids or bases on it. So she's rubbing some flower petals, and she's just rubbed China rose. hibiscus, and let's see. And she has rubbed a blue flower. So this blue flower is a pea flower. So this was wild pea near my house. So we have a red flower which is actually looking quite purple when on rubbing. And now she's putting, what are you putting, Manisha? Acid.
On the blue flower.
So acid on the blue flower is giving a very clear litmus-like conversion. So blue turned red very well. And now let's put it on the red flower, on hibiscus, on the left hand side. So this is also turning bright red. So because this is actually almost purple, it's not really red, it's purple, and with acid, with base now it's giving a bright green color. So the change of color is there for both cases, but different kind of change. And here also green with bases. So both flowers gave green color with bases and red color with acids. So this was like good because both flowers showed result, which is not always necessary. I mean, like we have discovered that many flowers will not show change in color. So friends, they have switched off the video and they're making preparation for a universal indicator, which we want to show you all the 7 colors of the universal indicator, preparing 7 beakers for it. The central beaker would be plain water, and 3 beakers on the left would be increasing concentration of acid, and on the right hand side increasing concentration of base. And this has to be done carefully because even a very little amount of acid or base can take the pH to 4 or 3 or 2, and or in the case of bases it can be easily taken to 10. So it's easy to get bright red color and bright purple color, but the intermediate colors have to be carefully monitored. So like how many drops you will put in water to get a weak acid or a weak base, that has like, it's like hit and trial. You have to do it through hit and trial, takes a little while, but if you do it, we can get a very beautiful range of 7 colors. It's very beautiful to see. It's like rainbow colors. So it's here you get a chemical rainbow. So that's what Manisha is currently preparing. So you'll have to wait a little. Till then, if you have any questions, or maybe we can take a break. Let's take a break. It's 12:15. Friends, let's take a 15-minute break. We will come at 12:30, right? So let's go, let's have a 15-minute break and we'll come back at 12:30. Till then, all our preparation will be done. So I'm just writing that. So friends, we are back and we are trying to show you, I mean, there are these 7 containers. Currently they have water, plain water, and actually ideally we have to take RO water because even tap water turns out to be slightly basic in our case, but in your place, if you check, some it may be slightly acidic or slightly basic. So actually RO water would be generally purely neutral. So now Manisha is adding indicator to all these glasses, and then she will add a few drops of few drops of acids or bases, more or less depending on how dilute she wants. In very dilute solutions, she will put very few drops, and for a stronger solution she'll put more drops of the same, and for this also she has had to take very dilute acid and very dilute base, because it's hard to get these 7 colors unless you take a very dilute solution. Because for example, even ordinary vinegar is a weak acid, still it will give you bright red color. I mean, vinegar means I'm talking about household vinegar. Household vinegar is already diluted acetic acid. Still, that gives you bright red color. So you need to do a lot of dilution actually. Currently, she's just putting universal indicator and what you are seeing as green. So now in front of you, she has put dilute acid in the two beakers. So in one, she's generously putting, because we want bright red color there. So I think we have got quite a good red color in this one. And the other one, she put a little acid. And the glass rods you use will also need to be, both are showing nearly the same red color. So probably she will need to make it like for color less than red, I mean for orange, she will need to use even less acid. She tried it just in the break, but even then, you know, this can go wrong, because at times, like, it's much more than needed or much less than needed to get these all these pH values. It's almost like hit and try. So anyway, we'll try doing. So now on the right hand side, now she's putting an alkaline solution, NaOH. That is a base. So it's easy to get the two extremes, dark purple and dark red. But even in between, we are getting purples only. Central वाला भी तो मिला देना. The glass rod should also be clean, otherwise that glass rod itself makes the solution acidic or basic. So right now we have nearly only 2 colors, but we'll try getting all the colors if possible. Of course, I can show them to you on a photograph, but seeing them in front of you is actually interesting. So here she has been able to get the yellow color, which means like much less acidic than the red one. Then there is one green, there's a darker green in the center, which is water. I mean, with strict control, you can get it better. I mean, but of course, first you do hit and trial, and then remember it, and then control it very carefully, how many drops you would add, and drops of dilute acid and dilute base. And accordingly, you will get, so here's a light, very light purple color. I mean, earlier she did in test tubes, then she got the 7 colors, but that test tube you pour inside the dark color. So we have a range, except I think the orange we didn't get, and also the one which is like in bases, which is right next to neutral water. I mean, some other color should have come. It seems as if like it's just very light purple. So meanwhile, I'll show it on my screen. I mean, see, this is what the scale tells us, that this is roughly the range of colors you are supposed to get. 7 being neutral and green, but then light green, yellow, orange, and red. On the other side, blue, dark blue, and still blue black, and then now we have got orange. At least she's still trying. Meanwhile, I am simply discussing. Basically, indicators are showing the less or greater presence of hydrogen ions. So basically, indicators and even pH scales are only talking about hydrogen ions, presence of hydrogen ions. And as you can see, like litmus is a very common and very popular indicator, easy to use as liquids and as paper as well. Then of course, turmeric is available in every home and gives a bright red color, as we saw. Then of course, there are different kinds of flowers. Here we have put in a flower which is hydrangea. On the left hand side, you can see hydrangea flower. Something very interesting about hydrangea flower is the color of hydrangea that you get depends on the kind of soil you have. Acidic soil will give a different color, and a basic soil will give a different color. So the same hydrangea plant will change color as per soil. So it's an indicator in another sense. And of course, the hibiscus, we saw that gives a good color. So from there, actually, we will come to the question of what are acids and what are bases. If Manisha is ready, then we will show. Manisha, shall we show? So, okay. I will stop sharing. So you can see Manisha's range of colors that she has got. So at least orange is better than earlier. So the acid range we have got quite well. The base range is not so good. Uma Sharma is saying it happens in her garden as well. So anyway, here we can see the glass rod hata dena, then we'll take a picture. Once in this trial, we got very beautiful, all the 7 colors, but like doesn't, like you can see that it doesn't happen every time. One has to keep trying. But even the indicator bottle shows, Manisha, show the scale on the indicator bottle. See, indicator bottle also, bring it in front of the camera. It also gives you a range of colors to match with your solution for you to judge what is the pH. So you can see against the color, a pH is written, and you can match and check what pH you have in a particular solution. So we can see yellow, green, light green, darker green, and then there are different shades of blues, right? Okay, friends. Thank you, Manisha. Can we enlarge the screen on the experimental table? See, all we can do is bring the camera very close. So please try. We will See, because, but if you want to see all the 7, almost that is all what the screen is showing. So you can show from top also if you want. Yeah, or okay, show them in close up, all of these. So from the top, from the side, in close up, the different colors. And show them from the side also, bringing the camera very close. Side se, matlab aise. Yeah, so you can see the colors very clearly. Okay, right? Okay, thank you. So we are now stopping this one. So friends, now after all this, we get to the question of what are acids? I mean, technically acid is a very important category of chemicals. We'll soon say why, but how are they formally defined? So can anyone tell me what are acids? What would be the formal definition of an acid? No answer, friends. See, I will not see sour taste and soapy touch are some of their properties, but see why then we can have substances with sweet taste, substances with salty taste, substances with other taste. So taste is not the characteristic of an acid. What I mean is it doesn't define an acid. So only taste is not why we consider acid is important and why we use them and why we teach them. Then we should be teaching other tastes also. So that's not what defines an acid. As Prema has said, acids are substances with H plus ions. H plus ions in greater concentration than ordinary water. So yeah, or in other words, the same thing can be said, pH less than 7. So anything which has higher concentration of ions, H plus ions in ordinary water would be an acid. Yes, so these are chemicals which give hydrogen ions. And of course, in blue litmus red is an indication of an acid. So concentration of H plus ions is the correct answer. Okay, so yeah, a lot of you have said this. So acids are substances that increase the concentration of H plus ions in a solution. Increase from a neutral status, neutral water status. So more hydrogen ions as compared to water. That is acid. Okay. Or we can say they decrease the pH of the solution. pH of the solution they make the solution less than 7 pH. Right? And they have normally, because acids are ionic compounds, they have this kind of structure. pH lower than 7 and it will be H and X. So H is a positive ion and X would be some negative ion. It could be any negative ion. So these two combine together to give an acid, and we know the common acids are HCl. So H is the positive ion, Cl is the negative ion. Similarly, H2SO4, 2 H plus ions and then 1 sulfate ion, SO4 ion, which is like a complex ion. So 1 sulfate ion, which is negative. So the word acid itself has come from sour. I mean, this I forget which language, probably Latin, but the word acid means sour. So what sour things can you think of around you in your daily life? So here's a good question. Okay, somebody has said Latin word is acer. Prakash Sharma has asked, acids are not only ionic, none of the acids are covalent. I'll just take that question. Okay, so around us, lemons, curd, what else? Lime. Lime, actually, lime in English is used for tuna, or what we call as just slaked lime and all. So lime fruit may be acidic, vinegar is acidic. All lemon and orange fruits, citrus fruits basically. Curd, yes. Tomato, raw mango, unripe mango, cherry tomatoes, tamarind, pickle, amla. Correct. So these are common acids in our, and many of the things that we eat, these are organic acids. So somebody has said, how about, is acid always an ionic compound? See, acid must give H plus ions. So even if rest of the acid has covalent bonding, for example, in sulfate, SO4 will be covalent bonding, but sulfate ion and hydrogen ions would have ionic bonding. So some amount of ionic bonding has to be there, without which the H plus will not dissociate from the negative ion. So the two ions must dissociate, which requires that there is some amount of, so yeah, somebody said grapes. Yeah, so see, like ionic bonding ensures that the ions break up in aqueous solution. When you dissolve something in water, if its ions break up, then it's an ionic solid or ionic substance. So that's true for acids. All the acids dissolve in water, and all acids will give H plus ions. So they are, and the sour things, as you people have, here's a child making the typical face when it's too sour, but some acids around us, you people have named vinegar, ketchup, because ketchup also has vinegar, so ketchup is sour. So this is acetic acid. Then citric acid exists in citrus fruits and also added to jams and jellies. Then, then we have lactic acid, which is present in curds, so develops in milk. So all kinds of dairy products have lactic acid. Then we have ascorbic acid, which we know as vitamin C, and it is very good for our health. And ascorbic acid is in citrus fruits and amla and many other fruits. Even green chili has ascorbic acid. Then carbonic acid is interesting because when you dissolve carbon dioxide in water, a very weak acid is generated, which is called carbonic acid, H2CO3. So that is there in cold drinks. It has a slightly sourish taste. So all cold drinks where you have which is like carbonated, utric acid in nettles, tartaric acid in tartary, oxalic acid in tomato. Yes, correct. Thank you. So yeah, people are giving many other examples. Yeah, so and many of these are organic acids. Right now I'll not get into what is organic or not, but anyway, in our life, organic things are those which are coming from living beings. So, okay. And now we come to what are bases. So bases are substances that decrease the concentration of H plus ions in solution by increasing the amount of OH ions. What will happen is, if you increase the OH ions, then many H plus ions which were already there in the solution will combine with OH to make water. So it's like H and OH also, there's a reverse combination also. No, you remember I had said that H2O breaks up in H and OH, but the reverse is also true. H and OH ions together can keep making H2O also. So they can recombine also. So if any substance increases OH ions in the solution, so that means more OH ions will attract H plus ions towards themselves, and this H plus and OH minus will make plain water. So the number of H plus ions will actually decrease. So that's why they increase the pH of the solution. So pH increases beyond 7. So it becomes 8, 9, 10, 11, 12 like that. So that's what happens if you add more so people are still giving examples of acids like hydrogen H2SO3 in rain. So when we have acid rain, of course we have uric acid in our urine, etc. So, but now have you understood this? Why increasing OH ions will reduce the number of H plus ions? I mean, does that make sense? Because this is an important idea. Why bases reduce H plus ions? Bases directly do not do anything to H plus ions. They just add OH ions. But more OH actually combine with H plus ions to give plain water, I mean neutral water. That's why when you add bases, the pH goes up. So it becomes 10 to the power minus 8, minus 9, minus 10, minus 11, minus 12 like that. And in solution, bases can be also can exist in solid state. But when they are in solution, they release OH ions, and there they are called alkalis. Alkalis are necessarily soluble or in solution. So the bases would have this structure. So one positive ion, which can be anything at all. For example, we have NaOH here. So Na is the positive ion, OH is the negative ion. Then we can have magnesium hydroxide. So magnesium is the positive, Mg plus is the positive ion, and OH minus is the negative ion. So they can have this kind of structure. Here we can make a visual demonstration with paper clips. So Manisha, will you show that? We have organic acids, we have organic bases. Yes, of course. We have organic bases also. Alcohols are actually organic bases. So organic bases will also give OH ions. And bases at our homes, I mean, I should have asked you. So, I mean, what are usual bases in our households? Some examples. Soap. Yes. See soaps are soap, toothpaste, baking soda. Yes, baking soda is a very good example. Washing soda also, window cleaner. Both kinds of soda are bases. Yeah, mostly these only. Even the lime or like with which we whitewash our walls, that is calcium hydroxide. Detergents, but friends, like many detergents and soaps are today making their alkalinity less, because alkalinity is not very good for our skin. High alkalinity actually is harmful for skin. So what they do is they make it less basic or less alkaline, and that's why some soaps will not give a good haldi test, the good turmeric test. If you try, sometimes it may happen either your turmeric is fake, or it's possible that the soap that you are using is not very alkaline. Wood ash also has base. So actually, with wood ash, you can actually make soap. Some people do that when they don't have an alkali. Soap is made by boiling alkalis with fat. So, but if you don't have alkali, you can like uh, take out the solution. I mean, put wood ash, try making a solution, and the clear part above that you get, if you take that, you can make soap out of it, because that's alkaline. So sugar, no. Wood ash, yes. Yes, like Roji is saying, people used to wash clothes with wood ash. Yeah, that's true, because it's basic. So bases actually are kind of soapy. So correct. So actually, friends, मैं यहाँ दिखा दूँ. So friends, actually, मुझे red वो देना. This is like
water.
अच्छा, okay. See, why we use paper clips is these are only for children. See, for children, especially in early chemistry, if you use paper clips, it helps them a lot to understand, because see, here we have used red paper clip for O and white ones for H. So this is H2O. So, I mean, if I say that water breaks up into its two different ions, so this is H plus ions and this is OH ion, right? Now I can show that HCl. So for HCl, I will say that the H plus ion here has gotten added with another Cl negative ion. So this makes HCl. So this is HCl. I mean, this is an exercise purely for, helping children understand, because paperclip illustration is extremely good for children. See, children are helped immensely if you use concrete objects instead of only words or symbols. And here, MG क्या है ये?
Magnesium hydroxide.
Okay, so Manisha has made magnesium hydroxide. So see, this is like, see, she has made like two. So she has used purple for magnesium, and OH, two OH are there. So like red is oxygen and white is hydrogen. See, this is enough. So see, we are just showing you because it's a good classroom exercise. And in fact, for reactions, showing reactions, this is extremely useful, because you can show that old molecules in a reaction, reactants break up. So you can open these up and recombine to make new products. So that idea becomes so clear, and balancing of equation also becomes so clear. So all this is extremely useful. Okay, friends. So now we go further after we have said